Okay, we've got some tangent line approximations is what we're going to do. So these are approximations, right, which means they're not going to be correct. They're going to be approximately, which is okay, good enough for government work, right? We're not sending rockets to Mars or anything. We're just doing math in class. So let's find first by writing the equation of our tangent line. So we need to figure out what is the y value when x equals 2. So what is f of 2, right? This is our y value, right? So we're using the equation y minus y1 equals m times x minus x1, okay? Or, you know what, I was at a calculus training and they all wrote theirs like on the as plus y1 here. Okay, oddly enough, they didn't use point slope form directly. They had the y1 added to this side. And this was the equation that they wrote. So if you want to do that, that's fine. If you want to leave y1 over here as a minus, that's also fine. But calculus AP is now getting into the plus over here on this side, solving for y directly. So the y value when x is 2 is 12 minus 2 squared, which is 8, right? 12 minus 4 is 8. And then we need to find the slope. And we find the slope by taking the derivative. Okay, slope is derivative. The derivative of 12 minus x squared is negative 2x. So negative 2 times positive 2 is negative 4. Right, so our graph has a slope of negative 4 when x equals 2, right? I guess that's the tangent line. So we can write the equation, right? We're going to write it in the new calculus form of y equals our slope of negative 4 times x minus our x value is 2, right? Our x value is 2. Plus 8, because that was our y value that we found, so plus 8. So that is how calculus wants you to write the equation of the tangent line at a given point, right? So here's your x coordinate, there's your y coordinate, this is your slope. So it says approximate, let's see, what else does it say? Use the tangent line to find the linear approximation. Okay, as in we are using a line to approximate a curve, right? 12 minus x squared is a curve, right? It's a parabola at the point x equals 2. So we're going to use this linear line, right, our tangent line, to approximate the y value at 2.1, which is pretty close to 2, so hopefully it's going to be pretty good. So we just have to take 2.1 and plug it in for x. I want to plug it in for x. Now, let's split hairs here. Y is not equal, y is approximately, right? We're using an approximation, so we're going to use our squiggly equal signs, not our exact equal signs. Not equals, just approximately. Y is approximately negative 4 times 2.1, right? That's our that's our x value that we're going to be approximating. Minus 2 plus 8. Okay, so we replace x in our linear equation that we just made, and now we do all of our math. Negative 4 times 2.1 minus 2, well that's 0.1, plus 8, which is negative 0.4, plus 8, which is 7.6. Okay, so that's our approximate y value. We are approximating the y value at 2.1 using this linear equation that we made. Okay, so then the third part says, determine if the approximate value is an overestimate or an underestimate of the actual value of your function. Okay, so let's just do this real quick. What is actually f of 2.1? What is 12 minus 2.1 squared? Okay, and this is where we need our calculator, unless you're a genius at your squares, which some of you might be. I personally am not a genius at my squares, so I don't know what 21 squared is. So I'm going to use my calculator. So our actual value, right, when we plugged it in is 7.59. And my approximate value is 7.6. So is my approximation above or below? Above. So this is an overestimate, not by much. Overestimate has an E, estimate. Right, so then we can look at the error. How much of an error do we have? Well, I had 7.6 as my approximation, minus the actual of 7.59. So how far off was my answer? 0.01, right? 1/100th is my error, right? Which is good enough for government work, as they say, right? Pretty good. 1/100th off, right? That's 1 penny. You estimated it was going to cost $6,849. It actually costs $6,848.99. Pretty good estimation, if you would. So that's what we are doing here. We are using our equation to do some estimating. Let's look at number 3. That one looks interesting, doesn't it? Of course not, but we're going to make it interesting anyway. Okay, when x equals 0, so our y value, the y value is f at 0, which is the natural log of 1 plus 0, which is natural log of 1. Okay, natural log of 1. Our calculator will tell us what that is as a decimal in a minute. But then your slope, how do we find the slope? We take the derivative and we find it at 0. So what's the derivative of natural log of anything? Right, that's 1 over the anything. So 1 over 1 plus x times the derivative of 1 plus x, which is just 1. Right, so in essence, I don't need to do that and multiply by 1. But just to make sure we have the chain rule, anytime we have a natural log function that we're deriving, it's always a chain rule. 1 over our argument times the derivative of the argument, which in this case is 1. So when I plug in 0, 1 over 1 is 1. Okay, so this has a slope of 1. So let's write our equation of our tangent line. Y equals 1 is the slope, so I don't have to write that. X minus 0, I don't even have to write that. So x plus the natural log of 1. Right, so I had 1 as the slope, x minus 0 plus the natural log of 1, right? That's formal. If you wrote it like that, that is still 100% correct. Okay, but when we simplify, x minus 0 is just x, and times 1 is just x, so x plus natural log of 1. So y is approximately 0.9, right? That's our new x that we're trying to find. What is the y value when x is 0.9? Plus the natural log of 1. And the natural log of 1 is 0, so it's approximately 0.9. So now let's go and let's figure out what it was exactly. So we're probably going to need our calculator for this. What's the natural log of 1.9, right? Because it's 1 plus x. 1 plus x is our equation, so we're going to plug 0.9 into right here. So 1 plus 0.9 is 1.9. So calculator says what for the natural log of 1.9? So this is what my calculator said. This is my approximation. Right? So we have approximately an error of 0.25 and change right there. Right? So it's always absolute value. Error is always a positive value. So is ours an overestimation or an underestimation? This is once again an overestimation. 0.9 is greater than 0.6418.
Coach, where did the natural log of 1.9 come from?
Okay, let's look at some of these trig ones. Oh, like number 5, that's a nice trig one. Tangent, that's one of my favorite trigs. Just kidding, I don't have a favorite trig. The y value, that's f at pi over 4, which is the tangent at pi over 4. So hopefully you know what tan of pi over 4 is. That's positive 1. At all the pi over 4's, tangent is 1 or negative 1. So the tangent at pi over 4 is 1. Right? You need to commit those to memory, the 45ers. So then our slope is the derivative of tan, which is secant squared. So I'm looking for what is the secant squared at pi over 4. Well, secant at pi over 4, that might be a little trickier than tangent at pi over 4. Right? Secant is the reciprocal of cosine. I know the cosine is root 2 over 2 at pi. Hopefully you know also that the cosine is root 2 over 2 at pi over 4. So then what's the reciprocal of root 2 over 2? It reduces to just root 2. So the secant at pi over 4 is root 2. And I need to do what to my secant? I need to square it, right? The secant squared of pi over 4. So first I find the secant value at pi over 4, and then I square that. Right? I'm not squaring pi over 4, I'm squaring the secant at pi over 4. So my slope is going to be positive 2. So now I can write my equation. Y equals the slope, which was 2 times x minus, my x value is pi over 4, right? They told us, they will always tell us your x value, plus 1, because that was my y value when x was pi over 4. Oh, that's not pi over 2. Mi siento. That's pi over 4. What was I thinking? Probably wasn't thinking, just writing stuff. So now let's approximate. Y is approximately 2 times, here's your value we're replacing x with, 0.75 minus pi over 4, that will be done in my calculator, plus 1. Okay, so I can write an equal sign here because I have an approximately here. Okay, because I am going to find out what this actually equals when I plug it into my calculator. So let's see, what is the tangent value at pi over 4? Right, because that don't, wait, not pi over 4. What's the tangent value of 0.75? From your calculator, what does that say? 0.9315. So notice 0.75 and pi over 4 are actually pretty close. Right, pi over 4 is like 0.78, and this is 0.75, so these two numbers are 3/100ths apart. So it makes sense that our approximation would be, in this case, 1/100th apart. So the closer your approximate number is to your given x value, the better your estimate is going to be. Okay, so let's figure out how we do that for some more calculus things over here. Okay, so this is something new that we're going to do to introduce a little bit of a differential equation. Okay, so we're going to do differential equations soon, but this is kind of an introduction to it. Introductions to differential. So we're going to write an equation for the change in y, right? This is delta y or dy. Delta y, maybe if you're familiar with physics, right? Change in y, which in calculus we write as dy. In terms of x and the change in x, so in other words, dx. Right? So that's what our derivative dy dx actually stands for, the change in y with respect to the change in x. How much are each of these things changing? So the first thing we want to do is find the derivative. right? So f prime is also dy dx. Is the same as y prime, right? There's so many ways that we can write a derivative. It's pretty important in calculus, so there's lots of ways to do it. So let's take the derivative of 2x plus 1. The derivative of this is 2. Okay? So then the only thing we have to do to put it in this form is get dy by itself. So how do I get dy by itself from this fraction? Well, I multiply both sides by my denominator. And I end up with dy equals 2 times dx. That's all there is to it. So let's see how we could use that. Let's do that with number 14. Approximate the change in the volume of a sphere. Okay, so that is dv, the change in the volume of a sphere. When its radius changes from 4 units to 4.1 units, right? So it says approximate. We could do this by using the formula, but we're going to use calculus and approximate it. Okay, so let's talk about how we do that. Here's our formula. The first thing we want to do is write the derivative of this formula. Okay, so dv dx, or in this case dr, because our variable is r, right? So not dv dx, but dv dr, because the variable in our formula is radius r. Okay, I mean, if you put x, that's not that big of a deal, but just know that your variables should be the same. Now, what's the derivative of 4/3 pi r cubed? Right, so there's your constant, 4/3 pi. What's the derivative of r cubed? 3r squared. Right, so this can of course be simplified. 3 divided by 3 is 1. So dv equals 4 pi r squared times dr, right? So if I multiply both of these sides by dr, I can isolate dv, and that's what I'm asked to do. What is the change in volume of the sphere? Okay, so now we've done the calculus. Let's do the plug and chug. Okay, what is the radius that I began with? The radius I began with was 4. So the initial length of whatever it is that you are studying goes in for your variable. Now, delta r is the change in my radius. So how much has my radius changed? 0.1. Okay, so your delta r is your change in the length of your radius. So I need to put all this into my calculator. 4 times pi times 64 pi. This is basically 6.4 pi is the change in my volume. So the volume is, of course, a cubic unit. So I don't remember what the units were, but 6.4 pi cubic units. That's how much my volume increased when my radius increased by 1/10. Okay, let's look at 15. So here's your function. Okay, so the first thing we have to do is take the derivative with respect to, I guess since r is your variable, we're going to find df dr. Okay, so let's first rewrite our fraction as a negative power, 0.01 r to the minus 2. Okay, so if you forgot how to take the derivative of a fraction with r on the bottom, then we write it without a fraction. So it's a negative exponent. So now I can use the power rule. My negative 2 multiplies by 0.01. Whoa, let's undo whatever that was. Okay, I pressed the wrong button on my explain everything. So this is negative 0.02, right? Because I do 2 times 0.01, negative 0.02, r to the negative 3rd power. Right, we always subtract 1 from our power. So this is going to become negative 0.02 divided by r cubed. And then, of course, we multiply by dr, and the delta r comes over here. Right, so this is our change in our, is this r, radius, is it r? Distance, right, distance between our two electrostatic forces. Okay, so now let's plug in what we know. We know that the radius was initially 20, right? So this is what we started off at. So that is your r value. And then, how much did my r change? It changed by 1. It changed from 20 to 21. Okay, so my delta r is just 1. So plug that into your calculator, and you get like a tiny number. I think there are 5 decimals and a 3 at the end. Right? 300 thousandths. Not very much at all. Okay, so there's 2 ways that we can approximate things. One is with a linear approximation, and one is by multiplying the derivative by the change of your variable. Okay, go forth and be awesome.